Hello guys, welcome to this new video. So this is going to be question 7 in the May 2023 Time Zone 1 paper 2. So here we're given a vertical rectangular loop of a conducting wire, and it is dropped into some magnetic field pointing into the page. And we are shown the loop as it leaves this region. And with reference to Faraday's law, we need to explain why there's going to be a EMF induced in the loop. So first of all, if we look in our data booklet, or we just know, Faraday's law states that the induced EMF is equal to minus n times the rate of change of flux over t. So if we have flux linkage changing through a loop, we're going to have an induced EMF. So here we see that as the loop falls, there's going to be less magnetic field lines going through the loop, and so the magnetic flux through the loop is going to change. And since we have a changing magnetic flux, we're going to have an induced EMF. So as it falls, less magnetic field lines through loop. So this means that the magnetic flux is decreasing. And this can also be thought of as the magnetic flux is changing. There's a changing magnetic flux. And so, according to Faraday's law, there is going to be an EMF induced. An EMF will be induced. And yes, so that is going to be the reasoning. And then we are told that just before the loop is about to completely exit this region, the loop moves with constant terminal speed v, and we're given some data, and we need to calculate this terminal speed. So first of all, let's think about why the loop is going to be moving at a constant terminal speed. So it's falling down like this, and we're told that it's just about to leave. So that means that the magnetic field lines are like this, just above it. So if we have something moving at terminal speed, that suggests that there is no net force, as if there would be a net force, then it would be accelerating and wouldn't be moving at a constant speed. But since it's moving at a constant speed, there must be no net force. So one of the forces we know that's acting on this is like the gravitational force, so Fg. And there's going to be a magnetic force acting upwards as well, which is going to cancel this out. F magnetic. And the reason this force is acting here is because if we use our right-hand rule, we will see that there's going to be a current induced in this part of the loop. And since there's a current moving in a magnetic field, this current is going to experience a force. So if we use our right-hand rule with our thumb pointing down, or our pointing finger pointing into the page, then we will see that there will be a current flowing this way in the loop. And if we use our right hand rule again, now with our thumb pointing to the right, our pointing finger pointing into the page, and then our middle finger will be pointing upwards, which is in the direction of this magnetic force. So that is why we're going to have a upwards magnetic force here. And since we know that we are moving at terminal speed, so no net force, so we know that the magnetic force is going to be equal to the gravitational force. This is how it's going to be in equilibrium. And let's see what formulas we have. We know that the gravitational force is just mg, so this is obvious. And then we know also from the data booklet that the magnetic force acting on a length of wire, so some wire like this, is equal to B times I times L, where B is the magnetic field strength, I is the current flowing in the loop, and L is the length, or in this case, the width of the loop of 15 centimeters. As here they show that this is the width. So we somehow need to calculate the current flowing in the loop. Well, we know that current is voltage divided by resistance. And well, here the voltage can just be the EMF. It's the same thing in this case. And well, we also know how to calculate the EMF, the induced EMF in some length of wire moving with some speed v. So we know that EMF is just BVL. This is also from the data booklet. And so this will be the magnitude of our current. So now all we need to do is plug this into this. And then we will have an expression with speed in it. So B times BVL over R times the length, like this. And then we just have to rearrange this for the speed. So if we do that, we multiply over with the resistance and divide by BL squared. And then we just plug all of this in. So the mass was 0.004 times G times the resistance, 0.025, yes, milliohms, so times 10 to the minus 3, and then divided by the magnetic flux intensity, 0.8, times the width, again converted into meters, and then squared, and this will tell us that the speed is 0.068 meters per second. So in this question, you just had to combine some equations to get an equation with the speed in it. And yes. And then the remaining parts of this question are about capacitors, and that's no longer needed for our syllabus. So yeah, I hope this was helpful, and see you in the next question.